Well, good morning, everybody, again, and it's my pleasure now to introduce our first speaker, who will be speaking on the subject of climate change, Dr. Euan Nisbet. Dr. Euan Nisbet has been working on modern greenhouse gases, especially methane in the atmosphere, but also on the early history of the Earth. He led the Natural Environmental Research Council's MOIA project to study atmospheric methane. And spent many years also studying early life and volcanism in Africa, Canada, and Australia. And he has written several books, one called The Young Earth, on the planet's early history, and another called Leaving Eden, on the subject of environmental pollution. So Professor Nisbet is going to speak to us this morning then on climate change, and I'll hand over to him.
Well, thank you very much for the chance to speak. If my slides come, I gather my slides are going to come up in a moment. Can somebody put them up? Great, wonderful. And yes, it's arrived. First of all, before I really start talking, an apology. I've, like many academics, have been talking to split audiences, a group of people in the room, and then a rather larger group of people somewhere in goodness knows where, and hi if you're in Australia. And then you get the problem that the people in the room can only read big writing, and the people long far away looking at their screens can read all the tiny writing and get very bored if there isn't enough of it. And so you compromise by putting too much writing up and then apologizing to the people in the room because they can't read it all, which is the situation where I'm in. So there is writing up here, but if you're in the room, please, it's the big picture that I'm after, not the little writing. Except this is very important little writing, but you'll know it off by heart anyway. That's Genesis. With that starter apology, we've got a planet of rainbows. The rainbow is something very, very extraordinary. If we didn't have the natural greenhouse gases, the natural temperature of the Earth is minus 18 or so. The planet's frozen. And yet we've got this wonderful planet of rainbows. And more than that, we've had rainbows for 4 billion years, even though the sun has been warming up as time has gone on. So something has been controlling this planet and making it habitable through billions of years. It's a very, very special place. It's unusual. And now we come along, and the messages that we have in the Bible is actually a challenge. We've all read Job, where he says, can you do this? Can you do that? That's not an insult, it's a challenge. We're meant to try. We're meant to grow to the stature of the fullness of Christ. We're meant to understand these things. We're meant to put a line across the universe. That's our task. And one of our biggest tasks is actually keeping this rainbow going. So, well, keeping it going, making it too hot. Let me try the next one. Now, how do I? Oh, that's come up. Sorry, I'm learning these gadgets. I'm very primitive. I grew up did my homework with a candle in school, and sort of, we didn't have electricity when I was a child. So, didn't have plumbing either. It's a long story. This is just a summary you can pick up from the Intergovernmental Panel on Climate Change, or lots of other places. To maintain a steady planet, what goes in has got to equal what comes out. What comes in is from the sun, and it's really high quality stuff, beautiful visible light, which actually is just right for DNA. Filtered on the way down because there are all sorts of things that take out the nasty radiation. What goes out is the infrared, but that bounces in the clouds, there's water vapor there, and eventually what goes out balances what comes in principle. Now, if you're lying in bed at night and you get cold, you pull on another blanket or a duvet or something, you get a bit warmer because you block the outgoing. And that's basically what the greenhouse gases do. And so we're blocking the outgoing. There's 30 plus degrees of natural greenhouse warming, from the natural greenhouse gases. Carbon dioxide and methane we're familiar with. Nitrous oxide is another one. The most important greenhouse gas is actually water, but that responds to the other ones by, you make the place hotter and more of that evaporates. But where could we be? We're in the water hole. Earth is extraordinary because at one end of the planet we've got frozen water. All over the middle of the planet we've got liquid water. And then in the air we've got gaseous vapor. We've got the three phases of water, very familiar to us. We see them throughout every year in Britain. Well, it doesn't always snow, but most of the time we see it. We see frost quite often. Most planets are either too cold or too hot. There's Venus. If you took the clouds off Venus, surface temperature is sort of 500 C. That's about what a cooking plate looked like in an old, before our kitchen stoves got modernized, used to have these cherry red plates. You put something on and it got hot. Go further out, of course, and everything's frozen. We're in the middle. More than that, as time has gone on, the sun has got hotter. Go back to the beginning of the Earth, and the sun's only 2/3 of the strength it is now. It's been burning hydrogen to helium, getting warmer and warmer slowly. And yet, Earth has stayed dancing in this little water hole. We've got sediments that are from Greenland, 3.8 billion years old, and they're clearly water-laid sediments. Some things maintain things. Now, in Genesis, the mist comes up from the earth and waters the whole face of the ground. Yes, it does. I took this pic actually in a place called Ascension Island, which is a marvelous little island in the Atlantic, where that mist is actually a wave hit a cave and has popped up. It's a volcano. And the mist on the planet, what's that? Well, there's water vapor in there, but the atmosphere as a whole is a biological construction. Apart from the argon, everything in the atmosphere is made by biology and maintained by biology. There's nitrogen, which is run by an enzyme called nitrogenase, and it's got a lifetime in the air of tens of millions of years, or longer than that even. Then there's oxygen. We still don't really know why the long-term amount of oxygen in the air is about 21%. It seems to be balanced by an enzyme called ribosco. In the short term, it's fires and things and plants that manage it day to day. And then there are the other things in the atmosphere, the water vapor, the carbon dioxide. It's a very, very well-managed system over time. That's the Garden of Eden. But it's a system that's quite fragile. Change things, and things can go wrong. Over 4 billion years, it's quite remarkable that it has stayed so steady. There have been huge changes. 2.5 billion years ago, the atmosphere was previously reducing, and then it became oxidizing. And initially a little bit of oxygen, now quite a lot of oxygen, built up in the air. There was a flip. The atmosphere is based on recycling. I apologize for this, but it's real. So, and the Bible doesn't avoid such things either. This is one of the most beautiful places in Switzerland, and those of you in the audience here cannot see this, thank goodness. But the Swiss just happens to be the local name for recycling. It's on the Greiner Pass, if anyone's ever walked up there, and you have to walk up there. It's a stunningly lovely place. It's very close to where St. Luke came over the mountains. The next pass along is the Luc Magnier, which is the great St. Luke Pass. Essentially, we're built on our own refuse. The entire biosphere is built by recycling our rubbish, our waste matter. And it's by recycling all the way that the planet has continued. Dung beetles are important. If we change the way we manage waste, then we're changing the planet. About 3 billion years ago, these beasties turned up. In most families, children have stuffed dinosaurs or something, or maybe stuffed rabbits. Sorry, not real rabbits, cloth rabbits, or something. My daughter chose a stuffed cyanobacterium. Well, she is a microbiologist now. So, the cyanobacteria turned up about 3 billion years ago. And they're quite remarkable because they photosynthesize. The early photosynthesis dealt with things like methane, which is a lot easier. It's still miraculous using red light. The cyanobacteria use two sorts of light, and they can actually take carbon dioxide and water, and then take carbon out of that, and then dump the waste, which is oxygen. Now, where does that waste go? It goes in the atmosphere. So the first few 100 million years, it didn't really matter. And then so much oxygen got in the air that the whole system flipped and became oxidizing. But they also do something quite remarkable in the middle, some of them. They can split N2, which is a very difficult thing to do. And they can fix nitrogen, and that tremendously increases the productivity of the biosphere. Now, cyanobacteria still rule. They have invented spacesuits, they're called trees. And they still essentially manage the atmosphere. We give out carbon dioxide, the embedded cyanobacteria in the trees, pick that up, turn it into organic matter, and then it just goes round and round and round. These are some drill cores that Natalie Gressner in our group looked at some while ago. These are Archean. And you can see some black stuff there, and you can see some sulfur as well. It's organic matter. It's organic matter that's 2.7 billion years old. And if you then look at the carbon isotopes, the carbon-12 to carbon-13 ratio, they're particular signatures of particular sorts of life. And from those signatures, you can actually pick up what was going on. And you can see that things like these cyanobacteria were operating. They were fractionating carbon. And there were other archaea, a different sort of microbial life, that was releasing methane from this. Methane, of course, very powerful greenhouse gas. So I'm interested in methane, so I'm going to talk quite a lot about methane now, unashamedly, because it's such a wonderful, interesting gas. These are some structures built by cyanobacteria 2.8 billion years ago. These are the great blobby things. The person in blue is actually a big guy. And you can see how big those blobby things are. It's dipping at sort of 70 degrees, so the original flat was that way up. And these blobby structures, they're equivalents of them living today. It took them some hundreds of millions of years, but they were the structures that eventually released so much waste oxygen that the atmosphere flipped into an oxidized atmosphere. And this, please do not read. This is just an illustration of just how complicated the atmospheric management is. Don't read it. It's just too complicated. We haven't a clue what all the balances are. But there is a system here that over billions of years has managed liquid oceans on the surface. And that's quite extraordinary, given that the heat has been going up all the time. And all sorts of things have happened. Now, one big disaster, but maybe it wasn't a disaster. If anyone ever goes up to Iona, which is the most marvelous place, I suspect some of the people here have been to Iona. Well, as you are around Iona, if you can, get a trip to the whirlpool of Corryvreckan, which is where George Orwell almost died, and the islands of the Garvalax. They're small little islands south of Oban. Could well have been the sort of hermit place that St. Columba went to. He had this quiet place. You'd think Iona was his quiet place, but no. He went off somewhere else to sit and think, and there are these little monks hermit little structures where they used to live. And those are the Garvalak Islands. They called them, St. Columba called it Himbak, actually, Himba. And as you come in, you see this extraordinary white lump in the rocks. It's called the Great Breccia of the Garvalaks. And it dates from the late Precambrian. The Earth's climate had a catastrophic event. It froze. And it must have come close to challenging the existence of life on the planet, because it pretty much froze over. It's called Snowball Earth. There may have been a bit of open water in the tropics, but basically it froze over. And then it went through these freeze-fry events. For millions of years, carbon dioxide came off the volcanoes and eventually got up to maybe 10% or so in the atmosphere. And then the greenhouse effect got so strong that it actually melted the ice. And of course, ice reflects sunlight. So if you change from a white planet to a blue planet, suddenly it gets incredibly hot if you've got 10% CO2 in the atmosphere. And so you fry. And so it went from freezing to frying. Dramatic changes. And from that, you got huge landslides and great big breccias and big lumps of stuff all over the place. That was the time when the oxygen went up, possibly by photosynthesizing all that carbon dioxide. And that's when animals begin. It changed the atmosphere again. So this catastrophe may well have led to a further change that led to something new, which eventually allowed us to appear. Because shortly after that is the start of what we know as the Cambrian onwards record. The point is, this is a very complex system. It does have catastrophes, but often those catastrophes lead to interesting follow-ups. Now, of course, the dramatic thing that's happened recently in geological terms is human beings. We're now moving as much Earth as the plate system, pretty much. We're completely reworking the surface of the planet. Several billion years of nature have, by setting the surface temperature, biology, life, keeping the surface temperature in the range of liquid water, has actually controlled the evolution of everything down to the core over the billions of years and maintained this plate tectonic system. Okay, what have we done? Now, this is where you get little fine detail, so please don't read the little fine detail. The top bar here, these are plots from the Intergovernmental Panel on Climate Change, from the SIX assessment, which is sort of coming out at the moment. This is from the draft that I was reviewing, but it's, I think this is now, you can quote it. This is from chapter 6, if you want detail in there, which is a really thorough look at what's going on in pushing the climate. And it's what human beings have added to the global greenhouse. The top bar there is carbon dioxide, that sort of yellowy bar at the top, orangey bar. The second one with a lot of orange is methane. That's the gas that I work on. And on the left is actually what it's doing and watts per square meter that we've added to the warmth of the surface. On the right is the change in the global surface air temperature that this has pushed. And the CO2 is about 1 degree, the methane is about 0.5 degree. Third one down is the nitrous oxide, the laughing gas, which is forgotten often by politicians, but it's pretty long-lived and it's actually very important indeed. It's another gas that we need to think about, and of course a lot of that's released by agriculture. And some comes off these wretched little steel canisters you see around all the campuses in Britain where people are getting legal highs from nitrous oxide, which drives me crazy. Okay, now this plot here is a plot of the Paris Agreement compliance. The flat line there is a line of a scenario that essentially is compatible with the Paris Agreement. And then if you look at the various gases, the red circles are what CO2's been doing. and lots of ups and downs and so on. It's more or less on line with what was expected. The reason for that, of course, is that basically nothing was expected. Everyone knew that when they signed the Paris Agreement, let's sign it now, but they worry about that in the future. So the Paris Agreement starts biting now, but when they signed it, well, they thought, well, let's worry about it later. Nitrous oxide is the blue one, and then the green one is methane. They did expect to do something about methane in the Paris Agreement quickly. It wasn't done. So methane is the gas that's furthest out of line with the expectations at the time of signing of the Paris Agreement. It's far out of line. And it's actually probably the easiest one to do something about. Let's see if I can get this up now. Oh, it's not coming up. Is that changing? There, okay. So this is the methane record. Our colleagues in US NOAA look hard at methane. It's going up, which is that top panel. Simultaneously, for 200 years, it's been getting isotopically heavier, which is going up in this bottom panel, getting richer in 13C. But when this recent rise started in methane, which is the top panel, it started getting isotopically lighter. We said, now, what's that telling us? That's what's driving the rise in methane. And this little seesaw here is the major sources of methane. On the right-hand side, which is which is upwards in that previous bottom plot, are all the fossil fuels and fires and so on. On the left-hand side are microbial sources. So go back to here. It's the microbial sources that are, it's not responding, that seem to be leading the rise now. What are the microbial sources? They're wetlands and they're cows. So we measure methane all over the planet. We get flasks from up in the high Arctic. It's the most beautiful place, up in Spitsbergen. We get them from the tropics. And methane is made by lots of different things. Wetlands there's about 600 million tons a year emitted each year. Wetlands are nearly 200 million tons. That's both the tropical wetlands, which are really important, and also the ones in the north. That's actually on the top left is the British equatorial wetland. You didn't know we had one. Charles Darwin planted it. It's about 3 meters across. It's on Ascension Island, but it really is. Gas, coal and oil, fossil fuels, a bit over 100 million tons a year. Ruminants, that's cows and sheep and so on, a bit over 100 million tons, also fires. So to do something about it, we have to figure out just what's been emitted and why. And so we measure around the planet. Our Moya project, which is just finished, was a big consortium of UK and universities and others, lots of international partners as well, measuring both in the Arctic and in the tropics, and also on this little island, Ascension Island, which is the UK's equivalent of Mauna Loa in the Pacific. We took our name Moya. Moya in Xhosa means air or wind or breath. Many of the Southern African languages, it means the atmosphere. But it also means spirit. And the original words of the South African national anthem, Nkosi Sikelel' Africa, how the chorus is "Descend, O Holy Spirit, Moya." So we were trying to look at the spirit of the air. We did all sorts of things. So I think it's not seeing my fingers. There we are. Okay, including sort of the UK research aircraft was a wonderful small plane flying around Africa, and in this plane. And actually having some rather big bumps. It was a bit scary at times. The plane went down to this wonderful place, Bangweulu. Nobody's ever heard of Bangweulu. It's quite important. It's where the First World War ended, when the German army laid down its arms in November, a week or so after November the 11th, on the Chambezi River, which drains into Bangweulu. It's the source of the Congo, so it's really important tropical wetland. It emits about as much methane as Britain. It's where Zambia's national hero, David Livingstone, died. It's part of the biological heartland of the planet. And when you fly over it, you discover it's got huge methane emissions. Now, we're changing that. This is pristine Africa, and yet all around there's been enormous changes to the vegetation. There's an enormous amount of deforestation. It's coppicing. If you wonder where the cuckoos have gone, this is where cuckoos spend their winter. There's also use of fertilizers, so that's going into the wetlands. All sorts of things are happening. Now, these flight crosses, you can probably see it, the very dark green blob, sort of center-leftish, is the lake itself. But these are huge wetlands here. The whole system about the size of East Anglia. And the red there is the methane emissions just coming out in huge quantities. This is what makes the planet work. Look at some of the other Zambian wetlands. Sorry about this. It's not seeing my finger. There. Please see my finger. Maybe somebody else. Okay. Some of the other Zambian wetlands, huge, these are Zambezi wetlands. The fish there, by the way, the Tswana word for fish is tilapia. You've probably heard of tilapia fish. Somebody, clearly from ancient Egypt, carried some of those into the Sea of Galilee. There's St. Peter's fish as well. How they got there, goodness knows. And the vegetation is what Moses encountered in his basket, papyrus. And so what we've been trying to do is work out the isotopic signature of these emissions. Now, why are we trying to do this? We're trying to work out how much of the planet's emissions are from biology, how much are from fossil fuels, and from that, what can we learn? Now, human beings need food, and tropical human beings get an awful lot of their food from cows, which comes from marginal land, from the land that you can't plow out. If you take those cows out of production, it's half the food supply. I have Indian relatives. India gets an enormous amount of its food from milk. How do we manage this? We're told in the Bible, don't muzzle an ox while it's treading out the grain. We have to respect our agriculture. How do we somehow balance our needs for food? And I'm thinking in particular of the tropics, the huge cattle populations in places like Ethiopia, South Sudan, and so on. How do we respect that? It's an enormous challenge for us. Do we just abandon pasture land and go to crops? Well, that's fine, but then you've got to throw a lot more fertilizer on it, and you've also got to chop down a lot of residual rainforest to grow those crops if you're going to plan on feeding everybody on that. How do we do it? These are huge challenges. And Israel is wrestling with God. Maybe it's a challenge we've been set. Maybe we can grow from this challenge. Maybe it brings us together. If human beings are meeting together in Glasgow, it's actually forcing us to stick together. That's a productive thing. It's a good thing. So, ruminant food is incredibly complex. It's not clear what we should do with this. Now, you in the room can't read this, but basically I'm saying cattle and sheep emit a lot of methane. Okay, we're emitting too much of it. Well, the simplest thing to do is stop the coal and gas leaks, which is straightforward. But with cattle and sheep, you're talking about the food of a huge amount of the population. And it comes from the pasture land. So how do we tackle this? It's a problem for the church to think about. These trade-offs are very unsimple. If we just rewild Britain, well, that just means we've got to get our food from someone else. and plow up the Brazilian forest or something. Not simple. The same thing with wool. Sheep emit a great deal of methane. But if you don't use wool, well, you make clothes from synthetics, which is oil, or you go and irrigate a huge amount of cotton where you throw a lot of fertilizer on it, and then you get nitrous oxide out. Not simple. Not simple at all. In some ways, you could argue that lamb and wool from New Zealand is probably a lot better than the alternatives. Dairy too. Each one of these things has trade-offs, and those are challenges. The other things we can do, like reduce our gas leaks, reduce our coal leaks, we can bring methane under control. Here's an example of fossil fuel production. This work our team did in Queensland, in Australia, over coal seam gas. You can see there's enormous methane emissions. Now that's low-hanging fruit. You can stop that quite quickly. Very, very tough problems. And how do we make these balances? So there's a Christian challenge to try to actually think through it. Not just read what you read in the newspapers, that we have to shoot all the cows in India or something. We have to think through complex balances where the answers are not simple. And yet that's a challenge. As I said, I think the challenges in Job that we, can you draw a line across the universe? These are challenges, the things that make us grow. So we can certainly get rid of our landfill waste. There's simple things we can just cover landfills in, particularly in the tropics. They're very simple. But meeting these challenges is not going to be easy. It does have the benefit, it brings us all together. We do need to do things. What can we do? We can stop the gas leaks and the coal emissions. We can fix the landfills. We can stop wasteful crop fires and so on. We can eat sensibly, be less obese. Africa's obesity problem is bigger than its famine problem. Why should we do it? Well, it's very deep in the Bible, again and again and again. Moses is told you've got to enter the land, but the land has to have a Sabbath too. You have to respect it. It's not just something that you can just extract from. You don't muzzle the ox when you're treading out the grain. And that's repeated in the New Testament. You've got to respect the agriculture. Don't just take everything out. Don't harvest to the very edge of the field. We have been sent out of the Garden of Eden. But actually, our job is to manage the Garden of Eden. And that's our great challenge. And I think it's something constructive. It's something that we can do something about. This is taken below my wife's office for many years. She's retired from it now, but it was actually planted by George Darwin, as far as I can tell. He planted a vine and a fig tree. Her office used to be Sir George Darwin's bedroom. George Darwin was Charles Darwin's son, great astronomer. He was the guy who followed the Venerable Bede by finally figuring out the tides and all sorts of other things. And his room has now become Darwin College in Cambridge. And underneath there, he planted a vine and a fig tree. Why did he do that? Well, Zechariah. You've got to think of your neighbors. This is a symbol of peace. These plants, this is science, but it's something that can create peace. So my basic message is we do need to do the science. We shouldn't just do the obvious things, like sitting down in the middle of the M25. We shouldn't just attention seek. We should try to figure out why these things are happening and what should our ethical response be to it. It's a very, very complex challenge. It's a global challenge. It's a challenge that brings us all together. It's something that does allow us to grow. It's a huge challenge, but the result from it could be a very much better planet where we can sit under our vine and our fig tree. So somebody was saying, should we have children? In the introduction, yeah. Should we have children? Yes, of course. because they need to solve these problems. It's a God-given problem. We need to try to tackle it. So I'll stop there. Have I run over my time? So, okay, thanks, Paul.
Thank you. Euan, don't go away. You've left us a few minutes for questions. Thank you very much. Okay. I'm amazed that growing up without electricity, I hadn't realized that you were quite as old as that. But
well, my little bit of the mountains in Africa, okay. I remember when the first phone came, and good. I'm now, very elderly.
We have a few questions. And Mary's got the roving mic for the first question.
Got one from online. Just the person was asking why and how the change in 13C in methane is happening affects climate change, and what can we do about it, please?
Ah, dear. Okay, yeah. If you could go back to my slides, or never mind. We're using the 13C. Carbon comes in different forms. There's carbon-14, which is the radioactive form, which is very, very tiny. And then there's carbon-13, sort of 1% of the carbon, which is common stable carbon. And then carbon-12, which is the majority of carbon, nearly all of the carbon. And if you get methane-rich in 13C, it's a bit like having red methane compared to blue methane that comes from the other sources. So you can then use these to identify where the methane came from. You can use the hydrogen or deuterium as well. And carbon-13 is particularly rich in tropical plants like papyrus, or maize, or sugar. And if you live on cornflakes and sugar all the time, and I grind you up, I can tell you that, because you are what you eat. So if you eat an awful lot of maize and sugar, you're going to be very rich in carbon-13 compared to the standards. So basically, we're using this as a sort of detective process to figure out who's actually making the carbon, making the methane. And so you smell the methane in the air, and it may be very rich in carbon-13 in Zambia. You say, that comes from a papyrus swamp. It's that sort of thing. So what we're trying to do is work out all around the world where this comes from. It gets even more complicated because the natural sink of methane is something in the atmosphere, and that also does things to the isotopes. It's a very complex subject, but we are trying to track it down, and we think it's coming from the tropics, the excess. Yeah.
There's another question, Mary, for the mic.
You quoted a lot from the Bible, which unsurprisingly you're almost bound to. I suspect your reasoning and rational thought does not come from the Bible. Otherwise, if you took it literally, you'd only think the earth is, Bishop Ussher says, about 6,500 years old. Your rational thought, I would have thought, is much more from the Greek philosophy. You know what the Greeks thought about. St. Paul said the gospel is foolishness to the Greeks. How do we... I think it's very dangerous to just quote something from the Bible and saying, yeah, this is working out, because I think there are a lot of contradictions in the Bible, and that doesn't stop me being a Christian. So how do you hold those two things as a rational scientist, and rationality is very important, reason is very important, hold those two things together and sustain your faith? Yeah, that's what. Was the Milton quote from Paradise Lost? I imagine. Yeah, which I like. I like poetry, but that was what occurred to me. You can't take some of those statements literally as a scientific proposition. I think that's what I'm saying.
Right.
Yeah.
Well, there's separate questions here. First of all, you worry about. I'm an Archean geologist. If you look at the way that the Jewish philosophers like Philo of Alexandria and the Christians, the early Christians, St. Augustine, they didn't read the Bible in the King James Version in English. They read it in Hebrew, the Old Testament. You're talking about Genesis. And St. Augustine is very clear. Time is not the movement of a planetary body. Philo, his concept of time as a dimension is actually very, very similar to Einstein. He talks of putting 3 walnuts, gluing them together, and then you put a 4th one on top, and then you rotate it. You can't tell them apart. That's what Einstein said with the 3 dimensions of length, height, and depth, and then time on top. They're not saying it's 24 hours. That's essentially a heresy to them. Augustine and Philo, they are not seeing it as some sort of 18th century idea of 24-hour days. It's completely different. So, no, I dispute what you're saying about creation being 6,000 years ago. On the other hand, I do tell our students to celebrate the 6th when we had the birthday, whatever the 1000th birthday was. It's in October sometime, isn't it? I do tell them to celebrate Earth Day. Yeah, it's a good celebration. But no, so I would dispute very strongly what you're saying about creationism there. Now, yes, the Bible has messages for us, very, very deep messages, enormously deep messages. And it's wrapped up in this complex story of Israel wrestling with God. You are supposed to dispute with God. You are supposed to stand up against God. The Psalms said, again and again, Israel is disputing with God. It's wrestling with God. And we get injured sometimes when that happens. But that's our task. We have to ask ourselves these questions. Get into the New Testament, St. Paul says all creation is groaning. And Paul actually repeats some of these things about the length and the height and the depth. So no, do not believe the fundamentalists. I have some sympathy with my Islamic friends who say, don't believe those fundamentalists. That's not what we're teaching. It's likewise in Christianity. They're heretics.
Thank you, Euan. I think we're just running out of time, really, but thank you for that question. Something we could follow up later in the discussion, but clearly it's, to sum up, the Bible is giving us a very strong message that as humans we have a responsibility under God to care for our world, and it comes in poetic form all the way through, but when we get into the real essence of the meaning, He has given us responsibility to care for it.
Yes.
Yeah, that's right.
Yeah. And it's very deep, and whatever you believe about the details, that message is right through both Old and New Testaments.
To be followed up later.
Okay,
good. Sure. Thank you very much indeed. Okay. And we're going to move on to our next talk now. So.
I'm just buffering for about 30 seconds, so I'm just going to talk to you as if you're talking